Hello everyone, I'm Satoshi Funabashi from Waseda University, Japan. I would like to talk about our research in hand manipulation of multi-fingered hand with daily objects based on graph convolutional network and three-axis tactile sensing. In the background, the multi-fingered robot hand is capable of dexterous manipulation. On the other hand, the acquisition of tactile information for the contact states can improve the manipulation stability. So when we see the previous research on multi-fingered hand control, some studies achieved the dexterous manipulation by using deep learning, but there is little tactile info like this one. This research doesn't use tactile information, or this one use only for fingertips. So the achieved manipulation is limited, or the object was specific for the manipulation. On the other hand, when we see the other research which focus on using tactile information for the multi-fingered hand, which is actually our research, achieved the high object recognition rates by using CNN and also considering the position and the sizes of all the sensors. So in this research, we could use all the tactile information from the entire hand, but still it has a problem that the results are unstable because the size of the tactile feature is not uniquely determined by experimenter. Also, we also need to think like to recognize the softness and the slipperiness, the object properties, so that the robot hand can manipulate a variety of objects. But when it comes to multi-fingered hand, occlusion usually happens, so we still need to focus on the tactile information. So here we propose the motion generating method based on graph convolution network, GCN, and also property labels. So firstly, we prepare the graph convolution network so that we don't need to do the engineering of the tactile information in advance. And also we prepare the property labels to input the GCN so that the hand can change the manipulation motion according to the property of the grasped object. So firstly, we did a comparison of GCN structure. So as you can see, most of the models could generate a successful motion. But actually, when it comes to the final posture of the manipulation, only this one, which had the most number of the convolution layers or the size of the convolution layers, could achieve the most number of successful manipulations. So we confirmed that the larger the number of the GCN convolution layers and the larger the sizes, we could get the greater number of successful manipulations. Also, when we confirmed the features from the convolution layer of model 1, which is the most successful one, we could confirm that the network acquired the feature of the position and the robotic configuration and the tactile features like some middle finger, little index, and the palm. So we confirmed that it acquired a feature and then it could generate a successful manipulation. Also, we did an experiment on the deformable object, and as you can see, it did a successful manipulation. But when we add the correct labels, like this object is a deformable object, and then the final posture is like this, it doesn't deform. But on the other hand, when we add the wrong labels to the GCN, it does the manipulation, but when we see the final posture, it squeezes the object. Also, when we see the trajectory during the in-hand manipulation, when we add the wrong labels to the GCN, it generates always generate the higher forces. On the other hand, the correct labels provided low forces, but still it could achieve the successful manipulation. So we confirmed that using appropriate property label is effective, and the hand didn't squeeze the deformable objects. So here's the conclusion. Thank you for listening.